Download this code from codegive.com, link in the description below. OK, let's dive deep into create Bloom filter index in Databricks, covering its purpose, mechanics, limitations, practical usage, and a detailed code example. What is a Bloom filter index? A Bloom filter is a probabilistic data structure used to test whether an element is a member of a set. It's designed to be space efficient and fast for membership tests. The key characteristic is that it can return one of two possible results. Asterisk possibly in set, asterisk the element might be in the set. Asterisk definitely not in set, asterisk the element is guaranteed not to be in the set. Bloom filters are prone to false positives, saying possibly in set when the element is not actually present, but they have no false negatives. They will never say definitely not in set when the element is present. In the context of Databricks, and more broadly, data warehousing systems like Snowflake, BigQuery, and even some rdbms, a Bloom filter index is used to speed up queries that filter on columns containing a large number of distinct values, especially when those columns are not suitable for traditional indexes, like B-trees or hash indexes. Why use a Bloom filter index? Consider these scenarios. Asterisk high cardinality columns, asterisk you have a column with millions or billions of distinct values, example user IDs, product SKUs, session IDs. Traditional indexes on these columns can be very large and inefficient. Asterisk infrequent lookups, asterisk you don't need to frequently look up data based on these columns. The overhead of maintaining a full-fledged index might not be worth the benefit. Asterisk range queries not required, asterisk you mostly perform equality checks, example where user underscore ID equals sum underscore ID, rather than range queries, example where user underscore ID between ID 1 and ID 100. Bloom filters are well suited for equality checks. Asterisk data skipping, asterisk the primary goal is to quickly skip partitions or files that are highly unlikely to contain the data you're looking for. How Bloom filter indexes work in Databricks. Databricks uses Bloom filters as a data skipping mechanism. Here's the basic idea. 1. Index creation, asterisk when you create a Bloom filter index, Databricks creates a Bloom filter for each data file or partition associated with the table and the specified columns. The Bloom filter summarizes the values present in those columns within the file/partition. 2. Query execution, asterisk when you run a query that filters on those columns, Databricks uses the Bloom filters to check if each file/partition might contain data that satisfies the filter condition. 3. Data skipping, asterisk if the Bloom filter says definitely not in set, Databricks can safely skip reading that file/partition entirely. This can dramatically reduce the amount of data scanned, leading to faster query performance. If the filter says possibly in set, the file/partition is scanned to perform the actual filtering. Syntax, asterisk. The basic syntax for creating a Bloom filter index is. Let's break down the components. Asterisk create Bloom filter index, this initiates the index creation. Asterisk on table underscore name, specifies the table for which you want to create the index. Asterisk for columns, column underscore name 1, column underscore name 2, lists the columns to include in the Bloom filter index. You can specify multiple columns, a separate Bloom filter will be created for each combination of column values within a file/partition. Asterisk options, FPP equals desired underscore false underscore positive underscore probability, specifies the desired false positive probability. This is a crucial parameter that controls the size and accuracy of the Bloom filter. A lower FPP, example 0.01, means a lower chance of false positives, but it also requires a larger Bloom filter, more storage and more computational overhead. A higher FPP, Example 0.1, reduces storage and overhead, but it increases the chance of false positives, potentially reducing the data skipping effectiveness. The FPP must be a value between 0 and 1. Databricks optimizes this based on the number of distinct values in the indexed columns. Example with code. Explanation asterisk. 1. Create sample data asterisk. We create a PySpark data frame and save it as a Delta Lake table named my_table. This data frame has an ID, a user_ID, simulating high cardinality, a product_ID, and a value column. We save it as Delta because Bloom filter indexes only work with Delta tables. 2. Create Bloom filter index asterisk. The create Bloom filter index statement creates the index on the user_ID column of the my_table table. We set the FPP to 0.05, 5% false positive rate. Adjust this based on your needs. 3. Check query plan asterisk. The explain command shows you the query plan. Look for Bloom filter in the query plan output to confirm that the index is being used. Databricks Query Optimizer decides whether to use the index or not, based on statistics and other factors. 4. Measure performance asterisk. We run the same query, select asterisk from my_table where user_ID equals 123, with and without the Bloom filter index and measure the execution time. You should see a performance improvement with the index. 5. Clean up asterisk. It's good practice to drop the Bloom filter index, drop Bloom filter index, and the table, drop table, when you're finished with it to free up resources. Important considerations asterisk. Asterisk Delta Lake asterisk. Bloom filter indexes are only supported for tables that are stored in Delta Lake format. Asterisk storage overhead asterisk. Bloom filter indexes consume storage space. The amount of space depends on the number of rows in the table, the number of columns indexed, and the FPP setting. Asterisk maintenance asterisk. Bloom filter indexes are not automatically updated when the underlying data changes. You need to manually rebuild the index after significant data modifications, inserts, updates, deletes. You can rebuild the index using rebuild Bloom filter index on table_name. Asterisk not for all workloads asterisk. Bloom filter indexes are most effective when used on high cardinality columns in queries that primarily use equality filters and where you don't need strict consistency, because of the rebuild requirement. They are less effective for range queries or on low cardinality columns. Asterisk cost analysis asterisk. Always consider the cost/benefit trade-off. The storage cost of the index and the maintenance overhead might outweigh the performance gains if the index is not used effectively. Asterisk automated optimization asterisk. Databricks automatically manages Bloom filters. The FPP is just a hint. Databricks determines the optimal FPP internally based on the data. Asterisk statistics asterisk. Make sure your tables have up-to-date statistics. The query optimizer uses statistics to decide whether to use the Bloom filter index. Run analyze table_name compute statistics to update the statistics. Alternatives and when to consider them. Asterisk Z ordering, Delta Lake. If you frequently filter on multiple columns together, consider Z ordering the data. Z ordering physically organizes the data on disk based on the combined values of those columns, leading to much more efficient data skipping. Z ordering is generally a better choice than Bloom filters when you have correlated filters. You can use optimize table_names order by column 1, column 2, to Z order a delta table. Asterisk partitioning your data based on common filter criteria can significantly reduce the amount of data scanned. This is often the first optimization step you should take. Asterisk materialized views asterisk. If you have complex queries that are run frequently, consider creating a materialized view. A materialized view precomputes the results of the query and stores them, so you can retrieve the results much faster. Caching Spark caching can improve performance if you are repeatedly querying the same data. However, be mindful of memory usage. Best practices. Monitor performance. Carefully monitor the performance of your queries with and without the Bloom filter index. Use the explain command and query execution metrics to understand how the index is being used and whether it is actually improving performance. Test different FPP values. Experiment with different FPP values to find the optimal balance between storage overhead and data skipping effectiveness. Consider Z ordering first. Evaluate Z ordering as a first step, especially if you have correlated filters or are performing aggregations on multiple columns. Regularly rebuild. Rebuild the index regularly after significant data changes to ensure its effectiveness. Document your choices. Clearly document why you chose to create a Bloom filter index, which columns you indexed, and what FPP value you used. This will help others understand your design decisions and maintain the index effectively. By understanding the strengths and limitations of Bloom filter indexes, you can effectively use them to optimize query performance in Databricks and other data warehousing systems. Remember to test, monitor, and adapt your indexing strategy based on your specific workload and data characteristics.